In this video, we're going to learn how to calculate related rates with circles and spheres. So here's our first problem. A leaky shower head drips water on the shower floor, forming a circular puddle. If the radius of the puddle is increasing at a rate of 5 millimeters per minute, how fast is the area increasing when the radius is 20 millimeters? Now, before we get into the math, let's talk a bit about what's physically happening here. We have a circle, it's our puddle, and as time goes on, the circle gets larger and larger. We know this because we're told that the radius of the puddle is increasing at a rate of 5 millimeters per minute. So here we've got several sketches of what the circle might look like at different points in time. Maybe at t equals 1, time equals 1 minute, the circle is pretty small. But at t equals 2, it looks bigger. And at t equals 3, it keeps getting bigger and bigger and bigger, and it keeps on growing over time. The radius keeps elongating at a rate of 5 millimeters per minute. Now, the way we write this mathematically is we say that the rate of change of the radius with respect to time is 5 millimeters per minute. And do you remember what we call rate of change in calculus? That's just derivative. So we can say that dr over dt, the derivative of the radius with respect to time, is equal to 5. Just to gain a bit more intuition, imagine what would happen if dr dt were negative, say like negative 5. That would mean that the radius would be decreasing with respect to time, and thus the radius would be shrinking, and so would the area of the circle. If dr dt were 0, that would just mean that the radius is not changing with respect to time, and in such a case we would just have a circle of constant radius, so the circle wouldn't be growing or shrinking at all. But here we have a positive dr dt, and thus the radius of the circle is growing. Alright, great. So we know about the radius of the circle, but what about the area of the circle? That's what we really want to find. How fast is the area increasing when the radius is some particular measurement? Don't worry about the particular measurement just yet. Just focus on how fast is the area increasing. How do we figure that out? Well, what we really mean is how fast is the area increasing with respect to time? What is the rate of change of the area with respect to time? So what we really want to find is dA dt, where A is the area. So dA over dt equals what? That's what we need to figure out. Before we get into that though, what do we know about the area of a circle? How is it related to its radius? Well, we know that the area of a circle is just given by the following formula. A, area, equals pi times the radius squared. Okay, so the way we approach this problem is we take these two bits of information, dr dt equals 5 and a equals pi r squared, and we use them to pull apart this derivative, dA dt, into the product of a couple of derivatives that we can actually compute. So we're going to write this as dA over something, we don't know what that something is just yet, so we'll leave it blank, then times something over dt. Now, there are two ways to think about this step here. The first way is very intuitively just think about this like a rate conversion. If you wanted to figure out how many minutes there are in a day, you could use an intermediate quantity like hours. You could say how many hours are in a day, that's just 24, and then you could ask how many minutes are in an hour, that's just 60. So the result, how many minutes in a day would be just 24 times 60. So that's kind of what we're doing here. We want to try to find some intermediate quantity so that we know the rate of change of A, the area with respect to this quantity, and we know the rate of change of that quantity with respect to time. Mathematically, you can also think of this as trying to apply the chain rule. The chain rule says that we can treat derivatives kind of like fractions. If we take the derivative dA d something and then multiply it by the derivative d something dt, then the d somethings will cancel out from the denominator and the numerator, and we'll just be left with dA dt. So the key to choosing this intermediate quantity is we need to know the rate of change of A with respect to that quantity, and we need to know the rate of change of that quantity with respect to t. Now there's one bit of given information that's kind of staring us in the face here, and it's that dr dt is 5. That follows the same format as this second derivative in the product, d something over dt. Why don't we just choose that as dr? Because then we'll just know that dr dt is 5, and we can just plug that right in. Well, if we do that, if we fill this numerator in with dr, then we also have to fill this denominator in with dr. And do we know dA dr? Well, we're not given that, but hey, we have an equation relating a and r, so we can figure that out. So yeah, that's what we're going to do here. Let's fill in dr up top here and below here. So again, it's kind of like the dr's are canceling to just give us dA dt, but when we split it up like this, we actually know what dr dt is, and we can figure out what dA dr is. Okay, so let's go ahead and write this down. So dA dt is equal to dA dr, we'll figure that out in a moment, and whatever we get, we'll have that times dr dt, and we know that dr dt is just 5. Okay, so let's go ahead and use this equation, a equals pi r squared, to figure out what dA dr is. All we really have to do is differentiate both sides of the equation, and we'll get dA over dr is equal to the derivative of pi r squared with respect to r. Pi is a constant, so that hops outside. And then the derivative of r squared with respect to r, well, that's just an application of the power rule. So pi times the derivative of r squared, and the derivative of r squared is just 2r. So this comes out to, simplifying, just 2 pi r. So we'll go ahead and plug that in. dA dr is just 2 pi r. So just write that in here for dA dr, 2 pi r. And then multiplying this just comes out to 10 pi r. Let's go ahead and fill in our left side here. Okay, so that right there, that's the rate of change of the area with respect to time for any general radius when the radius has length r. So we figured out how fast is the area increasing at any general radius r, but in particular we want to find this quantity when the radius is 20 millimeters. And to find dA dt when the radius is 20 millimeters, all we have to do is stick in 20 for r. So we'll just put it right in here, substitute it right into this equation. So we'll have that dA dt when the radius is 20 millimeters is equal to 10 pi times what we're putting in for r, that's just 20. So that comes out to just 200 pi. And what are the units on that? Well, it's unit area per unit time. First of all, we know that time is just in minutes. And what's the unit area? Well, we know that the unit distance is millimeters, and area is just distance squared, so millimeters squared per minute. So there we go, 200 pi millimeters squared per minute. That is how fast the area of the circle is increasing when the radius is 20 millimeters. So there we go, we're done. Alright, here's the next problem. As a spherical scoop of ice cream melts, its volume decreases at a rate of 16 centimeters cubed per minute. How fast is the radius of the scoop decreasing when the radius is 2 centimeters? First of all, let's get a sense for what's going on physically here. We're told that the volume decreases at a rate of 16 centimeters cubed per minute. That means the volume is getting smaller, so the scoop of ice cream is getting smaller. And as the sphere gets smaller, the radius is getting smaller and smaller. So the radius is decreasing also because the volume is getting smaller. And we want to find how fast is that radius decreasing. Okay, so that makes sense. But now this is a volume problem rather than an area problem. So how do we do this? Well, the answer is it's really just the same method that we did for related rates with circles. First of all, we collect our given information. We're told that the volume decreases at a rate of 16 centimeters cubed per minute. So that gives us the rate of change of volume with respect to time. So that gives us the derivative dV over dt. The volume is decreasing at a rate of 16 centimeters cubed per minute. So it's decreasing, that means the volume is getting smaller and smaller. On the number line, it's traveling in the negative direction. So that means the rate of change is negative. So negative 16 is dV dt. If dV dt were positive 16, the scoop would be getting bigger and bigger, but that's not what we want. We want negative. Scoop is getting smaller. Okay, and what is it that we're trying to find? Well, we want to find how fast is the radius of the scoop decreasing. When the radius is 2 centimeters, don't worry about that just yet. Just think about how fast is the radius of the scoop decreasing. What derivative does that correspond to? Well, rate of change of radius with respect to time, that's just dr over dt. So dr over dt equals what? That's what we want to find out. The way we do this is, again, we just go ahead and pull apart this derivative. dr dt, we write that as the product of two derivatives that we actually know how to compute. So let's just go ahead and get that started. It's going to be dr over something, whatever that something may be, then times something over dt. Now, any candidates for that something at the moment? Well, again, it's just staring us straight in the face. dv dt, we're given what that is. So what if we just make this dv dt, then we can just plug in -16 for this derivative here, and then this will work provided that we can figure out what dr dv is when we plug in dv in the bottom here. So before we go ahead and write in our dv's, let's just think for a moment. Do we know about a relationship between r and v? R the radius, v the volume? Well, the volume of a sphere is a function of the radius. We know the volume of the sphere is just 4/3 pi r cubed. And this means that we can go ahead and solve for r in this equation and then differentiate it with respect to v, and we'll be all good. Great, so that's going to work. And let's go ahead and do the computations then. So plug in dv on top and on bottom here. Let's just take a moment to simplify this. Plug in our dv dt. We know that's just -16, so let's go ahead and plug in that -16. So times -16. And let's also figure out what dr dv is. So really that's just going to involve solving this equation for r and then taking the derivative. But before we go ahead and do that, let's just think for a second, is there a way to speed up the computations here? What we're about to do is going to be a little bit computationally intensive. First, we have to solve for r in terms of v, and then we have to differentiate r with respect to v, and then our result will be in terms of v, and then we have to convert this given radius into a volume and then plug that back in. That's a lot of work. Is there any way that we can do this faster? Well, yeah, why don't we just go ahead and compute dv dr first of all. That's pretty easy because it's just an application of the power rule. And then to get dr dv, all we have to do is take the reciprocal of both sides. And then our result will be in terms of r, so we can just plug in this radius right into the expression. So actually, that's a much faster way to do that. Why don't we go ahead and do that way? So let's go ahead and differentiate with respect to r. So we'll get dv over dr is equal to, constant comes out, so just 4/3 pi, and then times the derivative of r cubed. Derivative of r cubed is just 3r², according to the power rule. Now we can simplify this. The times 3 here cancels out with the 3 in the denominator, so this is just 4 pi r². That's what dv dr is. And now we just take the reciprocal of both sides. So just flip this derivative, dr dv, and then just flip the other side as well. 1 over 4 pi r². So now we'll take that 1 over 4 pi r², plug it in for dr dv in our expression here. So that's 1 over 4 pi r². Now let's just go ahead and simplify a little bit. So -16 over 4, that's just -4. So this is -4 over pi r². And we can kind of tell that we're on the right track because there's a negative sign that popped out. And the negative is going to be on a positive expression here. So that means our entire answer will be negative. And that's what we want because we know the radius of the scoop is decreasing. So a negative result will make perfect sense. All right, so let's fill in our left-hand side here. That's dr dt. And in particular, we want to compute dr dt when r is equal to 2 centimeters. That's our given radius. So when r is equal to 2, we just go ahead and plug that into our expression here for dr dt. So that's -4 over pi times 2², which is just -4 over pi times 4. 4 over 4 cancels, so that's just -1 over pi. And what's the units here? Well, r is in centimeters, so let's write that down. Centimeters per unit time, and the unit time is minutes. So -1 over pi centimeters per minute. That is how fast the radius is decreasing when its length is 2 centimeters. And our negative answer makes perfect sense because it's a decreasing radius. Its rate of change is negative. So now we know how to calculate related rates with circles and spheres. And in the future, we'll continue to get a lot of practice combining related rates with ideas from geometry, such as Pythagorean theorem, similar triangles, and so on.